This is lesson 4, and in this example we'll write our first VHDL program and implement it on an FPGA on the Nexus 2 board. The problem that we'll do is we'll implement these 6 gates: AND, NAND, OR, NOR, exclusive OR and exclusive NOR, and we'll have these 2 inputs A and B. Now this is the entire VHDL program that we'll use, so let's take a look at it in more detail. The VHDL program is made up of an entity and an architecture. Here's what the entity looks like. Each entity must begin with this library statement, library IEEE, and this use statement, use IEEE standard logic 1164.all. This is a VHDL program that's provided by the system and is in the folder IEEE in this library. These 2 dashes is a comment in VHDL, so example 1, 2 input gates is just a comment. The entity has the entity name gates2, and then it uses this port statement. And the port statement defines the inputs and outputs. In this case we have the 2 inputs A and B and the output Z. Now we use the statements in or out, the so-called mode, to say that A and B are inputs, and we use out to define Z as an output. The data type is of type standard logic, or standard logic vector 5 down to 0. Now what's standard logic? Well, standard logic is a type that's defined in this IEEE library. And in that library, a type, standard U logic, is defined that has 9 values. U means uninitialized, X means an unknown, 0 and 1 are the 0 and 1s you're used to, Z means high impedance, W is a weak unknown, L is a weak 0, H is a weak 1, and dash is a don't care. So these 9 values are all values that the inputs and outputs of your circuit can have. Now, the reason for this is so that you can resolve the case where 2 outputs are connected to each other. The type U logic is what's called unresolved, and a resolved signal provides a mechanism for handling the problem of multiple output signals connected to one signal. So standard logic is a subtype, which is a resolved standard U logic, and there's a big resolution table that tells you what's going to happen. So for example, if one output 0 is connected to an output 1, normally this would be a bad situation, but in this case the result is unknown. So if you simulate a circuit where this is the case, the unknown will show up. On the other hand, for example, if you connect a high impedance output to a 1 output, then the resulting output is 1. So these resolution tables are what define what happens of these standard logic types. Now, the AND functions have their own table, AND or the various gates. So here's an example of an AND table that tells you what the AND function is going to do if the inputs are any of the 9 inputs of type standard logic and the other input is one of these. Well, the ones we're interested in, of course, mostly are the 0 and 1 inputs and the 0 and 1 inputs, and here is the truth table for an AND gate that you're familiar with, where the output of an AND gate is 1 only if both inputs are 1. But this table tells you what happens for an AND gate for any of the other 9 possible inputs. So let's look at the architecture of the program. The architecture, which is the second part of the VHDL program, looks like this for our problem. And notice that we simply use these assignment statements for each of these outputs. And notice we use the signal assignment, less than or equal. So Z0, which is down here, you see is the output of the XNOR gate, is just A XNOR B. Similarly, Z5 up here is just A and B. Now, the statement architecture has a name. I call it Gates 2 here. You could call it something else. But this second statement must be the entity name, Gates 2. And then you list the statements, but notice that we always have to have a begin and end here, and Gates 2, that's this architecture name, Gates 2. Now, note that all these statements execute concurrently. That is, it's not like a program where first Z5 is calculated and then Z4. You could write these in any order and it would produce the same result. So, this is the entire program. I'm going to show you how you actually implement this on an FPGA in a minute. But first, you could simulate this using our Active HDL simulator. In the tutorial on using Active HDL, if you watched that video clip, you saw how to do it. This was the result. A and B are the inputs. We used clock stimulators. Here's a 0 and 1 for A, 0, 1, 0, 1 for B. So A and B go 0, 0, 0, 1, 1, 0, 1, 1. And the output for the AND gate is high only if both inputs are high. NAND is just the opposite of AND. The OR gate, remember, is 0 only if both inputs are 0, 1 otherwise. NOR is just the opposite. And the exclusive OR was 1 if A is 1 and B is 0, or if B is 1 and A is 0. Otherwise it's 0, and the XNOR is just the opposite. So the simulation works. So we're then ready to synthesize it. We're going to synthesize it to this Nexus 2 FPGA boards. We'll use these two rightmost dip switches for the inputs A and B, and then we'll display the 6 outputs, Z5 down to Z0, in these lower 6 LEDs. Now, there's a file called Nexus 2 UCF, which gives the pin number associated with the LEDs and the switches and all the other inputs, outputs. So this is a piece of this file, Nexus 2 UCF. So for example, LD sub 0, that is LED number 0, is connected to pin number J14 on the FPGA. LD7 is connected to R4. Switch 0, that's the rightmost switch, is connected to G18. Switch 7, the leftmost switch, is connected to R17, and so forth. Now, it's going to be convenient to use the same names for the LEDs, we'll always call them LD, and for the switches, SW, in all of our programs. We can then use this UCF file to define the pin numbers, which means we need to write a top-level design, I'll call it Gates 2 top, in which the entity contains the input SW, that is the 2 switches, 1 down to 0, 2 rightmost switches, and the output LD, standard logic vector 5 down to 0. These are going to be the outputs. So we need to connect our gates to these switches, and we do that in the architecture for this top-level design. Between the word architecture and the word begin, we must include a component declaration of all the components we have, in this case just Gates 2. And when Gates 2, remember the 2 inputs were called A and B, and the output was Z. Then in the main architecture part of the top-level design, between begin and end, we use this port map statement. So we have the component declaration, and we have the component instantiation, where we define this label C1, an arbitrary label, Gates 2, that's the name of this component, and we use this port map statement, where on the left-hand side are the inputs and outputs of the component, A, B, and Z, and on the right-hand side we write down what they're connected to. That is, these are the inputs and outputs of the top-level design. So A is going to be connected to switch 1, B to switch 0, and Z, which was standard logic vector 5 down to 0, gets connected to LD, which we defined in the top-level entity as being also 5 down to 0. So we can just set Z to LD. So this is the top-level design.